have one more type of energy to tell you about, and that is internal energy. This is the energy associated with temperature. So it's like the heat, it's the vibrations, the motion, the molecular scale motion. So we could also call it the microscopic molecular motion of the body. And although you can think of it as microscopic molecular motion, we're a little bit beyond mechanical now, beyond just mechanical energy. But we can still write this equation. External work is the change in the kinetic energy plus the change in the potential energy plus now what we'll call the change in the internal energy. So what this is saying is you can still apply the idea of conservation of energy. We're just adding one more form. So if there's no external sources of energy, if we just have an isolated system, yes, you can have internal work exchanging energy between these, but the total will remain constant. Or if something outside does work on it, then you could increase. So that's the same statement, type of statement we had before. We've just added one more term. Let's see where internal energy can come from. Let's look at this pendulum right here, right? So we have a pendulum, yet another one, and it's oscillating back and forth. And we've studied this. The system is the pendulum and the Earth, and it's exchanging between kinetic and potential energy. Now I'm going to bring in a block at a little bit of an angle with a rubber mat on it. And you know what's going to happen is the rubber mat will have a friction force with the pendulum bob. So let me bring it in, and we just get the pendulum moving reasonably here. And I'm going to bring it in like this. And you can see it stopped the mass. Where'd the energy go? Well, let's draw this and see if we can figure out what happened. At the beginning, we just had pendulum way out here, and it was about to start coming down. And here we have the block, right? At this point, it's all potential. It's all gravitational potential energy. Actually, it stops here, so I'm not drawing a velocity on it, and it's about, in the next frame, it would start coming down. At this point, the mass is here, and it's just about to start interacting. It's straight down. It's just about to start interacting with the block, right? Here, it's all kinetic, right? Because now it has a velocity like that. Nothing's happened with the block yet. And then finally, what happens here is it's moved onto the block a little bit, and it's feeling a friction force from the block. So there's a friction force like that, and the block feels a friction force from the mass, like this. They both feel a friction force, and it slides along the block with some delta x, like we've talked about, some displacement. So clearly there's some transfer of energy, there's some work done here, right? So the mass pushes on the block pushes on the mass, and this is where internal energy comes in. So the friction force does work to convert the kinetic energy to the internal energy. And it does it as heat, right? It stops the mass, and all its kinetic energy is turned into heat. And then the heat dissipates into both the mass, the block, and the mass. The heat goes away. So if we take the case that our system is the pendulum and the Earth and the block, then we will conserve energy, right? So here's the system. There's the Earth, right? It's got the block in there. It's all in there. Here's the Earth again. In this case, block, Earth, like that. In all three cases, we include all three elements: pendulum, block, Earth. And if we think about the energy, here it was all potential, here it was all kinetic, and here it's all internal. because all that energy was just converted into heat. And the mechanism that allowed it to happen was a friction force. Friction was the work that let us convert with internal work from kinetic to internal energy. So this actually tells us a little something about the friction force, how it's kind of special, right? Other forces, the gravitational force and the spring force, were conservative forces. So Fg and Fs are conservative, which means you always get the energy back. You can always get it back. If you move something, push it up against gravity, you've given it some potential that you can get back as work. If you push something against a spring, you're giving it spring potential energy that you can get back. But F friction, that we've talked about some already, is not conservative, is non-conservative. Basically, you lose that energy. Once it goes into internal energy and heat, you can't really get it back in a mechanical system. If you get into thermodynamics, there's ways to get it back. But in this sort of level, we sort of think of it as lost because the work was done by a non-conservative force. Another property of these forces that makes them different is these depend on position, and this one often depends just on sort of normal force and velocity, this sort of a thing. Like the friction force doesn't depend on position. It just depends on these two things moving against each other, the dynamic friction. So in thinking a little further about energy, we got to kind of a new kind. It's kind of different from the potential, and the forces that create it are kind of different. But the expression to calculate it, the work, it's still just F times displacement, just the friction force times delta X, and that's the amount of work you would do to generate internal energy.